last class, we have seen what is the meaning of length of an interval. So, given either a closed interval or open interval, a semi-open or semi-closed, or infinite interval on the set of all real numbers. So, we have seen how we define the length. Now, the notion of length can be extended to any type of successive real numbers. So, in order to measure length for any arbitrary set, we define the general notion of length, which we call as the measure. ഇനി നമ്മൾ ഒരു മെഷറിൽ ഉണ്ടാവേണ്ട ഐഡിയൽ പ്രോപ്പർട്ടീസ് നമുക്ക് കണ്ടു. Now all those properties cannot hold, so we cannot construct such a measure. So we will look for measures where some of the properties are weakened. Okay. So we ideally define measure to be set function m such that m of e must be defined for power set of r. So the domain has to be power set of r. So that is not always possible. We cannot define a set function m which is defined for any arbitrary subset of r. So we will be weakening that condition. Then when you take the measure of an interval I, so that must give me the length of the interval, and it must be countably additive. So it must be countable additive. That means, so when we take m of if sequence e n, if they are disjoint sets, so when we take m of union e n, that must be equal to summation m of e n. So in the last property we have seen was that m must be translation invariant. So these are ideal properties of measure, but all this cannot hold. So we will be defining measure by weakening few of this properties. Now നമ്മൾ കാണാൻ പോകുന്ന measure നമ്മൾ define ചെയ്യുന്ന, so we are going to define measure as a countably additive set function defined on as sigma algebra script m. So script m will be a sigma algebra on r. It will not be entire r, but we will be taking a sigma algebra m. So the measure is defined as a set function on the collection script m, where we are going to take script m to be a sigma algebra, and it will satisfy these properties. So measure of an interval will be length, and it will be countably additive. So m of union will be equal to summation of e, and n will be translation invariant. So our domain here, so the domain of this set function is going to be some sigma algebra script m of subsets of r. So this is how we are going to define our measure. Let's now move on to define a measure. So first we will look at what is called the Lebesgue outer measure, or simply outer measure. So we will first define what is the Lebesgue outer measure. So let me take a set A. So A is any subset of real numbers. Now for any subset A of real numbers, so I can find a collection of open intervals, say In. So In is a collection of open intervals, so which is covering the collection of open intervals that covers A. Meaning നമ്മൾ covering എന്ന് പറഞ്ഞാൽ that means A must be contained in union of I n. Now this sequence In, that is a collection of open intervals. So for each In, its length is well defined. So L of In well defined ആണ്. So L of union of In will be equal to summation L of I n. Now A is contained in unions I, N. So if you look at the measure of this set A, so the length of A will be less than or equal to length of this entire collection. കാരണം A is contained in union I, N. So measure of the outer measure of A will be, so we are going to look at how do you define the length of A. So the measure of A will be less than or equal to length of union of IN. ഇനി A എന്ന് പറയുന്ന സെറ്റിന് നമുക്ക് ഒന്നിലധികം കവറിംഗ് ഉണ്ടായിരിക്കും. So we can choose any arbitrary covering. So an open outer measure of A is defined to be n star of A. So that's how we denote the outer measure. So n star of A is the infimum of all such values. അപ്പോൾ നമുക്ക് A's പല കവറിങ്സ് കണ്ടുപിടിക്കാം. For each covering, I can find out the length of covering. So n star of A, and the outer measure of the set A is defined as infimum over all the coverings. So infimum over all union IN summation of length of I. So the infimum of all such length, summation of the length, that is defined to be Lebesgue outer measure of the set A. Now as you can see, when you take an open interval, each length, the length of IN നമ്മൾ എടുക്കുമ്പോൾ, so for any open interval IN, so length will be always greater than 0. So n of IN is always greater than 0. So summation n of IN has to be always greater than 0. So this is always a non-negative value. So therefore the infimum of summation n of IN will be greater than 0. So you can see that actually n star of A will be greater than 0. So since summation of n of IN is greater than or equal to 0 for any collection IN of A, so we will have union of infimum of summation n of IN, so that will be greater than or equal to 0. Now this is what we define to be the measure. So therefore n star of A will be greater than or equal to 0. So the outer measure is A, that will be a number which is greater than or equal to 0. Now we will look at a few properties of n star. So the first property is n star of 5. So for an empty set, its outer measure will be equal to 0. So let us prove this. So the proof is as follows. So let us take any A belongs to R. So for any A belongs to R, then when you take the set AA, that will be an empty set. So open A, that will be equal to 5. So we can write it as, we can write A, we can write, so we can have 5 contained in A. So therefore AA will be a covering of 5. The covering 5. Therefore n star of 5 will be less than or equal to length of, so by definition n star of A will be infimum of length of the cover. So n star of 5 will be less than or equal to length of A. Length is defined to be the difference of the endpoints for an open interval, so that will be A minus A, which is equal to 0. So therefore n star 5 is less than or equal to 0. So here you have less than or equal to. So let me call equation 1, but 5, the definition of outer measure നമ്മൾ ആദ്യം കണ്ടു n star for a will be always greater than or equal to 0. So n star 5 has to be greater than or equal to 0. So n star of 5 less than or equal to 0 and n star of 5 is greater than or equal to 0. So combining 1 and 2 gives, so therefore n star of 5 is equal to, so that is the first. So let us look at the second property of the measure. The second property is, if A is contained in B, then n star A will be less than or equal to n star B. So if A is a subset of B, then measure of A will be less than or equal to measure of B. So let us look at the proof of this result. So we will start with a collection In of open intervals such that B is contained in the collection. So let sequence In be a collection of open intervals such that B is contained in union In. So this is an open cover for the set B. Now since as we know A is contained in B, so A will be contained in union In. So therefore the sequence In is a covering of A as well. So therefore m star of A, so by definition m star of A has to be less than or equal to length of union of In. So that will be equal to summation of I. Now by the definition of the measure, so m star of A will be less than or equal to infimum of summation of length of In. Now since the collection In is an open covering of B, so when you define the measure of B, so n star of B will be equal to infimum of summation of I. So this is the definition of measure of B. So let's call it as equation 1. So putting this in 1, so we will be getting m star of A less than or equal to infimum of summation length of In. So this is equal to m star B. So that implies m star of A will be less than or equal to m star B. So therefore if A is contained in B, then m star A will be less than or equal to m star B. Next property is X is singleton set, then we will show that m star of X is equal to 0. So first let us take an open cover of a singleton set X. So you can see that for any positive integer n, the singleton set X is contained in the open set X minus 1 by n to X plus 1 by n for all n belongs to n. So this will be a covering of singleton set X. So by definition m star of X will be less than or equal to length of X minus 1 by n to X plus 1 by n. അപ്പോൾ length എന്ന് പറയുന്നത് ഡിഫറൻസ് ഓഫ് n പോയിന്റ്സ് ആയിരിക്കും. So നമുക്ക് 2 by n കിട്ടും. So we will be getting m star of X less than or equal to 2 by n for all n belongs to n. Now take the limit as n tends to infinity. So we will get m star of X less than or equal to, the limiting value is 0. So m star of X less than or equal to 0 വരും. But as we know, measure is always greater than or equal to 0. So combining both, we will get m star of X equal to